Welcome back to class, everybody. Today I'm going to help you with the PhET molecular geometry simulation. There is a practice sheet in Google Classroom for you. Let me show you that really quickly. Looks like this, and it's got a place for you to fill out molecular formula, draw on Lewis structures, and give the name of the molecular geometry, and then sketch it with the angular geometry as well. All this information, you can get this from the PhET simulation, or you can get it offline. But I just wanted you to see how this works, because many of you using Chromebooks will have difficulty using this PhET simulation. So I'm going to give you some alternate tools to answer these questions and learn a little bit about molecular geometry. The reason molecular geometry is so important for us is that molecular geometry is essential to how molecules behave. And if we have one molecule that's got a shape, and we make another molecule that's got a similar shape, particularly in the fields of medicine, they sometimes have similar effects. So let's go ahead and look at the first one here. This is methane. I went to real molecules, and you'll notice down here these tabs, and I just selected from the drop-down menu methane. And if I want to know the bond angles, which is by far the most difficult thing to figure out on your own, I can click this button for bond angles. And if I want to know the molecular geometry, I can click this. And this shape, this it's kind of like a pyramid shape, boom, 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 is called a tetrahedral. Now there's something called electron geometry, and for molecules that have all of their electrons in bonds, the electron geometry and the molecular geometry are the same. And you'll see that on the worksheet as well, tetrahedral and tetrahedral. And there's bond angles. And those bond angles on tetrahedral compounds are always going to be around 109.5. If we have a two-dimensional diagram of something, and we take a circle and we want to make things equally distant around a circle, well, you're all familiar with that angle. This angle here between these two hydrogens is 90 degrees. When you take that, though, and you make it three-dimensional, make it a sphere, now not only can you distribute things around the outside of the circle, but you can push them toward you or away from you, and that allows an increase in the bond angle up to 109.5. So this angle is significant in three-dimensional geometry because it is the equidistant angle for four objects arranged around a sphere as opposed to a circle. I'm going to run very quickly through molecules and some of the other shapes. The second one on there is CO2, which is linear. You'll notice that all of its electrons are bound up, and so its electron geometry matches its molecular geometry. But if we get to something like water, its electron geometry changes. I can, if I do it just right, I can make this look linear this way, but it's not really linear. And the reason for that is these non-bonding pairs of electrons are going to influence the shape. You can do all kinds of things with these PhET simulations. You can put triple bonds in. You can give them expanded valences. Those are valences that are greater than the comfortable number of electrons, which for most elements is 8. You can add lone pairs, and you can make very strange molecules that don't really exist, but you can still look at their molecular geometry and find out what it is, and bond angles as well. If you can't get the PhET simulations to work, there is an alternative way for you to answer all the questions on this worksheet. you can type in Lewis diagram and then put the name of the element in. For example, CO2, you can see all of these. Now you notice this is a little bit different. This actually has the non-bonding pairs. One of the limitations of this PhET simulation, if you go back and look at it, is that while you can have it display non-bonding pairs of electrons on the central atom, it can't display the non-bonding pairs of of electrons on peripheral atoms, like these two oxygens here. So this is their model of CO2, and it's accurate for what it is, but it doesn't show what you need to answer the question for the Lewis structure, which are the non-bonding pairs of electrons on those oxygens. And those are key because these non-bonding pairs of electrons get it to that magic number of 8, that octet of electrons around the oxygen. We have 2 here, 4, 2 in this bond, and 2 in this bond are 6 and 8. You'll notice the carbon doesn't have any non-bonding pairs, and that's because it's got 4 bonds going to it, each with 2 electrons. So 2, 4, 6, 8 electrons. You can type in the name of the compound and look it up on Wikipedia. That will show you 3-dimensional models as well as Lewis structure missing the non-bonding pairs of electrons. But it will also give you bond angles. It will give you the geometry, and you can tell the electron geometry by looking for non-bonding pairs of electrons around the central atom. And I'm going to show you the last one of those really, really quickly. Ammonia. Ammonia is got 3 hydrogens bonded to a central nitrogen and then 1 non-bonding pair of electrons. And while it's tetrahedral in terms of the electron configuration, the same way that water was, it's got a different shape. This one's called trigonal pyramidal or trigonal pyramidal, depending upon who you want to talk to. You can see this triangle in the back, but you'll notice that these 3 hydrogens are bent downwards slightly, giving that central nitrogen a bit of a point to it, and that's where the pyramidal part comes from. That's most of the geometries that you're going to be focused on. I'll run through them again really quickly. We have linear, we have bent, we have trigonal pyramidal, and we have tetrahedral, like that. And that's most of what you need to know and be able to recognize for these. The bond angles will change. If I take and look at sulfur dichloride, for example, you'll notice that it's got different bond angles than water does, and that's because of the differing number of electrons both surrounding the atoms, but also the non-bonding pairs of electrons. This one's down to 103 degrees. So you can look up any of these angles. You're more than welcome to use the angles that are given by the PhET simulation as well. But you'll find if you go online, you can get a more accurate measure of those bond angles. Good luck with this new material. Keep up with the reading. You'll do just fine. Keep in mind that we're going to cover new material, but a lot less new material than we would in class. So if you're having any struggles, feel free to contact me on the message board or just shoot me something through Google Classroom or email. All right? Hope you all are well. Take care, and I'll talk to you again soon.